1-1 injective functions. Hello everyone. Today, we are going to begin our discussion on a fundamental concept in algebra, 1-1 functions, which are also referred to as injective functions. To start, let's look at the broader picture. In our study of relations and functions, we are often interested in the mapping process, specifically, how the elements of the domain, which are our inputs, are paired with the elements of the codomain, which are our potential outputs. It is important to understand that a function is not merely about the act of assigning an output to an input. We must also consider the uniqueness of that assignment. We want to know if the relationship between the input and the output is exclusive. Formally, a function f from x to y is called a 1-1 function or an injective function if every distinct element in the domain x is mapped to a distinct element in the codomain y. To put this in simpler, more intuitive terms, a function is 1-1 if no two different inputs ever produce the same output. Every single input has its own unique output. Throughout the rest of this lesson, we will move from this conceptual understanding to the formal mathematical definition, explore what happens when a function is not 1-1, and practice verifying these properties using algebraic methods. Mathematical definition of 1-1 functions. Now that we have established the intuitive concept of 1-1 functions, let us move on to the formal mathematical definition. To prove that a function is truly 1-1, we cannot rely on intuition alone. We must use a specific mathematical criterion. Mathematically, we state that a function f, mapping set x to set y, is injective if the following condition holds. For any two elements, x1 and x2, belonging to the domain x, if the function of x1 equals the function of x2, then it must be that x1 equals x2. To put this in simpler logical terms, if you begin by assuming that the outputs of two different inputs are the same, meaning f of x1 equals f of x2, and through algebraic simplification, you find that the inputs themselves must have been identical, meaning x1 equals x2, then the function is confirmed to be 1-1. Essentially, this test ensures that no two different inputs can ever produce the same result. In our next slide, we will explore what happens when a function fails this test, which leads us to the concept of many-one functions. Many-one functions. Now that we have established the definition of a 1-1 function, let's examine the alternative. If a function fails to meet the criteria for being 1-1, it is classified as a many-one function. To explain this more formally, a function is considered many-one if there exist at least two distinct elements, which we can call x sub 1 and x sub 2, belonging to the domain x, such that x sub 1 is not equal to x sub 2, but their images are identical. In mathematical terms, this means that f of x sub 1 equals f of x sub 2. Essentially, while a 1-1 function ensures a unique output for every unique input, a many-one function allows multiple different inputs to map to the same single output. To help you visualize this difference, we will now move on to some real-world examples and algebraic verifications in the upcoming slides. Real-world example of 1-1 and many-one functions. Now that we have covered the formal mathematical definitions of 1-1 and many-one functions, let us move to a real-world example to help you understand these concepts more intuitively. Consider the relationship between the citizens of a country and their government-issued unique identification numbers, such as a social security number or an Aadhaar number. To analyze this as a mathematical function, let us first define our sets. The domain, which we will call x, represents the set of all citizens. The codomain, which we will call y, represents the set of all possible identification numbers. The function, f, is the actual process of assigning a specific ID number to a citizen. Let us break down the analysis step by step. First, imagine we take two different citizens, person A and person B. Next, we check their identification numbers. Because these systems are specifically designed to be unique, person A's ID number cannot be the same as person B's ID number. Therefore, because distinct inputs, the citizens, result in distinct outputs, the ID numbers. This mapping is a 1-1 function. To give you a clear contrast, consider a different scenario. If we were to map citizens to their birth month instead of an ID number, this would be a many-one function. This is because many different people, who are our distinct inputs, will share the same birth month, which serves as the output. Understanding these conceptual differences is essential, as it sets the stage for the next section, where we will learn how to verify these properties using algebraic methods. Algebraic verification of 1-1 functions. Now that we have discussed the theoretical definition and looked at a real-world analogy, let us move on to the algebraic verification process. This is the formal method you will use in your exams to prove whether a function is 1-1 or not. Let's look at example 1, where we aim to prove that a function is 1-1. We are given a function f, mapping the set of real numbers to the set of real numbers defined by the rule f of x equals 4x plus 7. To verify this, we will follow a systematic step-by-step process. First, we start by assuming that two arbitrary elements from our domain, which we will call x sub 1 and x sub 2, produce the exact same output. Mathematically, we write this assumption as f of x sub 1 equals f of x sub 2. Second, we substitute the specific rule of our function into this equation. By replacing the function notation with the algebraic expression, we get 4 times x sub 1 plus 7 equals 4 times x sub 2 plus 7. Third, we simplify the equation to isolate the variables. We begin by subtracting 7 from both sides of the equation, which leaves us with 4 times x sub 1 equals 4 times x sub 2. Fourth, we further isolate the variables by dividing both sides of the equation by 4. This simplifies the expression down to x sub 1 equals x sub 2. Finally, we reach our conclusion. Because our assumption that the outputs were equal, f of x sub 1 equals f of x sub 2, led us strictly to the conclusion that the inputs must be equal. X sub 1 equals x sub 2, we have formally proven that the function f of x equals 4x plus 7 is a 1-1 function. Please pay close attention to this logic, as in the next slide, we will examine a case where this result is not achieved, which leads us to what we call a many-one function. Algebraic verification of many-one functions. Now, moving on to the next part of our algebraic verification. In the previous slide, we saw how to prove a function is 1-1 by showing that equal outputs must come from equal inputs. However, not every function behaves this way. Let's look at example 2, where we will prove that a function is many-one. Consider a function f, mapping the set of real numbers to the set of real numbers defined by the rule f of x equals x squared. Our goal is to verify if this specific function is many-one. Now, pay close attention to the process here, as it differs from the 1-1 proof. To prove a function is many-one, we don't need a general algebraic proof for all numbers. We only need to find one single pair of distinct inputs that produce the exact same output. This is essentially providing a counterexample to the 1-1 property. Let's choose two different values for our test. We will let x sub 1 equal 2 and x sub 2 equal -2. It is clear that 2 is not equal to -2, so we have two distinct inputs. First, let's calculate the image of x sub 1. When we plug 2 into the function, f of 2 becomes 2 squared, which equals 4. Next, let's calculate the image of x sub 2. When we plug -2 into the function, f of -2 becomes -2 squared. Since a negative number squared is positive, this also equals 4. Now let's compare our results. We observe that f of 2 and f of -2 both equal 4. Even though our inputs, 2 and -2, are different, they both map to the same output. Therefore, we can reach our conclusion. Since two distinct elements in the domain map to the same element in the codomain, the function f of x equals x squared is a many-one function. As we move forward to the next slide, I want you to think about whether this result would change if we weren't using all real numbers as our domain, as this is a very common point of confusion. Common mistakes to avoid. Now that we have covered how to verify these functions algebraically, let's discuss some common mistakes to avoid so you don't lose marks in your exams. First, be careful not to confuse the domain and the codomain. It is crucial to remember that the nature of the set you are working with completely changes the result. For instance, remember the example from the previous slide where f of x equals x squared was a many-one function? That was because our domain was the set of all real numbers. However, if we restrict the domain to only natural numbers, that same function becomes a 1-1 function. This is because, by removing negative numbers from the domain, we no longer have two different inputs that produce the same output. Second, some students mistakenly assume that if a mapping is not 1-1, then it is not a function. This is incorrect. Please remember that a many-one mapping is still a perfectly valid function. The fundamental requirement for any function is simply that each input must map to exactly one output. It is perfectly acceptable for different inputs to share the same output. That is simply what defines a many-one function. Finally, let's address the issue of insufficient proof. When you are asked to prove that a function is 1-1, you cannot simply plug in a few sample numbers, such as 1, 2, or 3, and conclude that the function is 1-1. Testing a few cases is not a formal proof. To be mathematically rigorous, you must use the algebraic method we practiced earlier. You must assume that f of x sub 1 equals f of x sub 2, and then algebraically demonstrate that this necessarily implies x sub 1 equals x sub 2. This is the only way to prove the property holds for all possible values in the domain. Key takeaways. Now, let us wrap up everything we have discussed in this lesson with a few key takeaways to ensure you have a solid grasp of the concept. First, let's recap 1-1 functions, which are also known as injective functions. As we saw in our introduction and the ID number example, a function is 1-1 when distinct inputs always lead to distinct outputs. In other words, every unique input has its own unique result. Conversely, we have many-one functions. As we observed with the birth month example and our work with squared numbers, a function is many-one if at least two different inputs map to the exact same output. To verify this algebraically, remember the mathematical test we practiced in our examples. A function is confirmed to be 1-1 if, by assuming that f of x1 equals f of x2, we can logically prove that x1 must equal x2. Finally, always keep in mind that the classification of a function as either 1-1 or many-one is not fixed. It depends heavily on the defined domain and codomain. As we discussed in the common mistakes section, restricting the domain can completely change the nature of the function. Review these points carefully, as they form the foundation for the next topics we will cover in functions.